What happens if I move? Okay. Okay, I'm John Menke, and I have known some of you all, either personally or via publications at various times. I guess David, I first met 20 years ago or so. I'd like to take a minute. Oh, it's there. All right. I didn't like when your head's going back and forth. I wanted to take a minute to give a little bit of my background, because my talk's not about what I've done, but about what you shouldn't do. So I should give a little bit of cred here. I'm a physicist, and I've always been interested in astronomy, and then at various times you go away and come back to it. And I started taking it much more seriously about 25, 30 years ago. I started out doing pretty pictures, and then got bored with that after a couple of years, started doing photometry and doing variable stars primarily and eclipsing stars. Then did occultations for quite a while. I've worked with Steve Kennard and others on occultations, mostly recording clouds, as we know, but I've had a fair number of successes as well. Along the way, I've always been interested in instrumentation, and this bears on my talk. Along the way, I also did a real-time aperture photometer to work on video, which nobody was interested in. Adirondack almost bought it, and they didn't want to do anything technical. And I also did a drift scan, GPS-tied drift scan microprocessor that would give ticks on the drift scan, so you could see what time was and which direction the damn thing was going. It's awfully easy. All this stuff is great in theory. You get out there in the cold and in the nighttime, 3 a.m., and everything is off. So I've done that stuff. Then got very interested in spectroscopy, built an 18-inch Newtonian, built a spectrometer, R equals 3,000 spectrometer, and my current project is a spectropolarimeter, which no amateurs, to my knowledge, do for good reason. And I'm not sure that I will succeed, but anyway, I'm working on that. So I got interested in this issue of video photometry, other than in general principles, as an outgrowth of trying to look at the JEE, at Scotty's JEE work last winter, to decide whether I wanted to do more observation this fall. And I'll be talking about that tomorrow. But that provided the impetus, because what I found was, in my opinion, is that work is afflicted with some photometric errors that are fundamental to it. And so then somebody here suggested that I give a talk on photometry with video cameras. What are some of the problems? And so that's the genesis of why I'm here. I do not have the last word on things by any means. And if I step on somebody's toes, I apologize, but go ahead and speak up, and then we'll deal with it. If I could have the next slide then, please. So if you're measuring time, you're doing timing, occultation timing. But if you're measuring intensity, you're doing photometry. Two completely different things, even though the equipment may look the same. Two different things, two different sets of skills, two different sets of concerns. Next slide, please. So what's the biggest problem using video photometry? LI movie. That's the biggest problem, because it makes it look so easy. You got the curves there. You got the ratios of the brightnesses. Hell, anybody can do photometry. Next slide, please. So hopefully I stepped on somebody's toes here. I got your attention. Software issues. But software issues with respect to using video for photometry. There are software issues because the software is not really suited for it. There's some fundamental problems. The hardware issues. Video cameras are not really suited for it. And the third and most important, occultation skills are not the same as photometric skills. So you may be a damn good occultationist, doesn't make you a photometrist, and vice versa. There are people who do photometry that think occultation stuff is easy. Try going out at 3 a.m. and getting there at the right minute and having everything work. That's not so easy. Next slide, please. So I'll go into some of these things along the way. So photometry, video or CCD, is not as easy as it looks. There are lots more sources of error in photometry than there is in occultation work. In occultation work, if you've got the damn star and it goes off and goes on and you've got the timing, you're almost done. I mean, it's not that simple, I know, but you're almost done. With photometry, because you're measuring the amplitude of something, you're doing an analog measurement, basically. Anything that affects the intensity of what you measure, the recording of what you measure, is a potential source of error. And we'll go into some of those. All of those have to be accounted for in photometry if you're doing it right. They don't concern you at all with occultation work. So photometry with video can be done. There are some people who say, no, you can't do it with video cameras. That's baloney. Of course you can do it. But it's hard to do. Every detail's got to be right, or else you can't prove you're right with the answer. And it is tougher than using the CCD cameras. And I'll get into some of the reasons for that. Next one, please. So the best way to do video photometry is don't. Don't do it. Use a CCD camera instead. Next one, please. Or photometer. Okay, I've done it. I've done fast photometry at kilocycle rates and stuff. That's fun too. So why not? Well, the observing system is the software, the camera, and the person. Okay, all three have to work right together. And I will talk about them somewhat separately, but they all have to work together. Next slide, please. First, talking about the software. Actually, there are two different programs you can use, as most of you know. Movie, which is the older one. That's what I've used for almost all my work. Then there's Tangra. It's a new program. Risto has written it. It's I think, a very elegant program. It's more advanced. Both of them are good for timing, no question about it. Tangra is probably a little better for photometry if you insist on doing photometry with video. So next slide, please. Incidentally, before I continue on this slide, this version, one chewing gum stick didn't work. I'm glad I brought two. At the very end, I will give a link to the website on Tangra in which Risto has written a 10 or 15 page paper on proving that his software will work for photometry and what the problems are doing photometry with a video camera. So I urge you, if you do any kind of photometry with a video camera, whether you use Tangra or not, go to his website. I'll show you the link at the end, and read his paper and then read it again. If you don't understand essentially all that paper, you don't know how to do photometry yet. And he brings up many of the same issues I do. I just saw this the other day. So it's nice to see some corroboration from somebody I really respect. Okay, so why isn't the video timing software useful for photometry? Well, it is useful. But one of the basic problems is it's hard or impossible to measure individual pixel values. You can get the pretty little 3D profiles of a star, doesn't tell you the values. You got to know the values. Is the value 127, or is it 128, or is it 230, or is it 240, or 255? You can't measure the values. It's hard to handle, and this is true of all video, it's not just the software. It's hard to handle long series. If you're trying to do photometry for a 10-minute something or other that's varying, that's not that big a deal. If you're trying to do an hour, you've got 100,000 frames. If you're trying to do photometry over many hours, you've got lots more. How do you handle all that stuff? You usually end up breaking it into pieces. It's very hard work to break it into pieces and analyze each piece with LI Movie or Tangra. The result is you make mistakes. And when you're 3/4 of the way through a complicated analysis, almost always, at least when I do it, I think, oh darn, I should have used a different setting on something. I should have done something in a different order. If you've got 4 hours of work already invested, do you go back to the first minute and do it over? You say, ah, to heck with it. That's what happens. That's the human part of the equation. So it's hard to handle long series. It's hard to use reference or companion stars. It's not built into the software. Photometric tools, calibrations like darks and flats and so forth, that's not built into the software. And it could be done, but it's not. And the software is usually not real time. All that you have real time with a video is you've got the video screen, the monitor showing what's happening. And that's not telling you very much because you don't have the values of the pixels. In contrast, when you do, how many of you all have done this? I don't want to insult anybody, but how many have you done? How many of you have done CCD imaging, real CCD imaging? Yeah, it's interesting. Not all hands went up. 40% of the hands went up. When you do a CCD exposure for 60 seconds or 5 minutes or whatever it is, you don't know what's going on during that time. You hope it's working. You come up with the image, and the software you use to take the image almost surely shows you those parameters right away. It shows you the maximum pixel, the histogram, and so forth. So that's almost real time. Hard to do that with video. Okay, so then we have some camera issues. These were the software issues I wanted to emphasize. Next one, please. Video cameras are complicated. It may only cost you $10 for one, or it might cost you 1,000, but they are all complicated. They may be deliberately non-linear. The gamma may not be equal to 1. And I'll go into some of this if you want in questions. They're designed, most of them are designed for non-point, mid-level brightness images. They're not designed for one little point in the middle of black. And the software, the internal firmware, the way they handle things, the electronics is not designed for a star sitting in the middle of black. Doesn't mean they can't be used, but there can be problems. When Risto did some of his measurements, for example, he took 164, most of us probably use 164 cameras. He took 164 to measure the linearity, and his showed a gamma of 1. That is, it's linear, more or less. It's linear. A friend of his said he had a 164, and he did a similar measurement, and it showed up 0.45. Same model, exactly the same model. So Risto gets the AVI file from the other friend, runs it through his analysis, and sure enough, it was 0.45. Same model. You don't see that with CCD cameras. You can't trust video cameras that it's linear unless you've measured it. How many of us have ever measured the linearity of a video camera? You have? Yeah, I don't think any of us have. I haven't. I did measure linearity of a CCD camera. I was very impressed, but okay. Auto exposure algorithms. A lot of the cameras we just use on faint objects, and we assume it's going to go we're going to go as deep as we can go. But you're trusting an auto exposure system. You don't know what that thing is doing during the exposure. If the exposure changes for whatever reason, that's changed your calibration. That means the intensity of what you read out isn't going to be right. Your photometry is going to be wrong. Still works for timing. Doesn't work for photometry. The readout itself, the electronics and the analog to digital converter, may not handle a star on a black background properly. And have you ever proved it, that it does? High readout noise. If you do an hour of video, you got 100,000 images. You've read out 100,000 images compared to, say, a dozen 5-minute images on a CCD camera. They're not exactly equivalent in noise, but you've got to have more noise from 100,000 readouts in the end result. And finally, there's limited dynamic range. Almost all of our video cameras are 8-bit, or at least we process the analog into an 8-bit, and versus a 16-bit and a CCD. And I emphasize CCD cameras is not twice the band, twice the resolution. It's 256 times the resolution. That's a huge difference, and that can affect results. Next slide, please. So for bright targets, and I haven't talked about this part yet, for bright targets, saturation and roll-off are an issue. So lower right, we have input light intensity going across, output video level going up. Of course, the linear ideal is a straight line with some slope to it. When we get up to saturation, can I step off the X? When we get up to, that's all right. When we get up to saturation to 255, it's okay. When we get up to 255, of course, you won't get any more out indicated, even though there's more input. But shy of that point, we have what I call a roll-off, which could be from a variety of causes, but in general, CCD cameras show the same thing. There will be a reduced accuracy, a change in calibration, however you want to say it, before you get to saturation. Say the top 20%. A lot of our cameras are anti-blooming, which we try to ignore, but that adds to the roll-off in general. So those can be effects, and you do not know what those effects are. When you look at the output, you can't really go backwards and fix that. I've shown this little canary over here. If there's, and this has a bearing on tomorrow's talk on the JEE, if there are any saturated pixels in the target of interest or in your comparison star, I'll get to that in a minute, that's a canary in a coal mine. You've got a problem. It means you're up close to the saturation limit, at or close to the saturation limit, and you don't know what the response is at that point. If you're trying to do accurate photometry, you'll either be wrong or you at least can't prove you're right because you're not in a linear region. Next slide, please. Okay, this is, for example, this is a image of, this is from tomorrow's talk, but it's an image of one of the Io satellites. In fact, it's in saturation, and you can see the 255 level on the left-hand graph. This is, I'll tell you how I get this in a minute. So we take a cross-section through the image, and sure enough, there are at least 2 pixels saturated, unknown number of pixels near roll-off. You can't see that in LI. You could probably detect that in LI movie if you looked at that frame. But you got 100,000 frames, or 10,000, or whatever it's going to be. Next slide, please. Okay, I'm going to just anticipate a little bit one of the issues tomorrow, because I don't want to overstate this either. This is the elephant in the room, the JEE. How many of you are familiar with the JEE debate? Not everybody. Okay. Maybe things aren't as awful as I thought. JEE is Jovian extinction event. This is a observation by Scotty of a dimming of Io as it crosses, or of the combination of Io and Europa as Io crosses in front of Europa. And that has photometric implications. He was doing a photometric measurement without quite realizing it, I think. In any case, he had unique challenges there. One is that the satellite images are bright. They're 5th magnitude. When's the last, well, I guess some of you guys, except for Regulus, you do observe sometimes bright stars, but usually they're not very bright. Very rarely. So he was observing bright stars. The occulting image was changing shape as the measurement was going. It was going from 2 to 1 PSF. The occulting image was changing with time, and it was getting brighter, not dimmer. None of those things are we as occultationists, we're not comfortable with those things. So it's not rocket science, but they're unusual situations. So that's when, but this does bear on photometry. Next one, please. We'll talk about more of those. We'll talk about that tomorrow. But sometimes video is the only way. It might be an NEO, for example, or flares or something like that you're trying to look at. This is for photometry. Or it might be there's just no other instrument available, and you use what you got to use. So how do you avoid errors? Next slide, please. Well, you got to learn photometric methods. If you're going to do it, you got to learn them. You don't have to learn everything in all of its detail, but you've got to know pretty much what the deal is. If you know generally how photometry should be done, then you may at least be able to say in a given observation, which are the things about photometry I have to do right, which are the things I can ignore. And that's part of the game too. You got to practice. You can't just go out and expect it to work. You got to do the dry runs and the real runs. You have to apply it rigorously. It's a quantitative measurement, so you have to be accurate. You have to know all the relevant characteristics of the sensors. I've been talking about linearity. That's very important. You need to use the appropriate tools. You need a linear camera. You need to use good software, including photometric software, I'll talk about in a minute. You need to be skeptical about your results. It's so easy to put errors into photometry. How many people here have done photometry? Okay. How many of you done full transform, full sky photometry with transforms? You're better people than I am. I've done that twice. I did with CCD. Okay, that's even better. But most of the time I'd try and pick a photometry job that I can do without going through all the rigmarole. No, I never said that. No. You can, but you can. If you can use a CCD camera instead of video to do your job, use the CCD camera. That's where I am. Okay, and be skeptical of your results. There's so many mistakes. You got to look at that data every which way, looking for errors, looking for anything that looks funny. And if it looks funny, it's probably wrong. Next slide, please. There are many sources of error. I'm going to take a minute on this slide. Obviously, nonlinearity in the camera or anywhere in the system, including in the software, can do it. I'm still in the X. Okay. Saturation can be an issue for brighter objects. Yeah. If the exposure varies during your observation, that obviously can cause a major change in your calibration. That can happen because the field, maybe some clouds come through. You keep going. The clouds produce enough brightness, if you've got sky brightness like we have down here, that it actually changes the exposure that the camera thinks it's going to put on. That's part of the issue. You don't know what's going on, but that's what it's doing. You may have gain that's unstable. You always are fighting noise. In the astronomical source of problems, of course, there's the darn sky. Unfortunately, we have an atmosphere. And so we have to deal with clouds and contrails and all the rest of that stuff can be affecting the intensity that you're going to measure. The altitude of the target. Down here, it's going to have blue absorbed in the atmosphere compared to when it's up here. Its color changes as it goes down. Its brightness changes as it goes down, even for a given color, as the extinction changes as it goes down the atmosphere. There is scintillation that's creating noise that's independent, of course, of the brightness. It can be a color mismatch between the target and the response curve of the camera. You can have dew. We keep ignoring dew. That can happen and changes the calibration of your system. When you do the analysis, you can use an improper comparison star. You can use inappropriate software. All those things can cause your answer to be wrong. I'm not trying to make you fearful about photometry, just respectful of it. Next one, please. Well, that's only one of the evil ones. Okay. One of the keys, coming back partly to the person part of the system, you have to use software that allows you individual pixel measurement and easy analysis. If your software that you're using to gather the data and analyze the data is hard to use, not because it's badly designed, but because it's not appropriately designed, and there is no good appropriate software for video photometry. If it's hard to use, it means you're going to make mistakes. You're going to take shortcuts. You're not going to redo the measurement when you really should. So that's a key element. You really have to have a reference, a comparison star, a comparison satellite, some reference for brightness that you can compare your target to. Because if a contrail passes through your field of view, for example, or a cloud passes through, or your gain changes, if both the comparison and the target change the same amount, then if you do the difference between the two as a differential photometry, then the error pretty much gets canceled out. So a reference star or a reference object is really crucial in doing photometry. I mean, if you don't have one, you got to go find one. So if there's not a good comparison within the field of view, maybe you have to move the field of view keep going over and measuring that comparison star, and then coming back. That's a pain in the neck. It's a source of error. If there are clouds coming through, you're really going to get mixed up as to what's going on when you're doing this. Unfortunately, in Maryland, we do not have photometric skies very often. Linear response range. Ristos shows that 164s have nonlinearities at the top end, and guess what? And I was surprised at this, at the low end as well. Very surprised. Whether you need to take into account the transformations, the color matching of the reference star might be a different color from the target star, which feeds all through the color response of the camera. Do you need to take that into account or not for your measurement? If it's a 10-minute measurement, you don't need to worry about that. If it's a 2-hour measurement, you probably do. Finally, you got to document every step. Every single thing you do. If you don't have a logbook, you're out of luck. You really have to keep track of what you're doing. Which filter went in when? When did you take this exposure versus that? When did you move to a comp star and check it and come back? You need to have all that recorded. Next slide, please. So you can use the occultation software in LI to compensate for its limitations, and or you can use what I call photometric software, like MaximDL and CCD Soft. How many of you have ever used either of those programs? Okay, 4 or 5 people, but most of you have not. Okay, these programs, MaximDL and CCD Soft, are 2 programs you have to purchase. I think there's some freebies there. I'm not sure how good they are. But the photometric program is designed to run CCD cameras, to take to take images, and to measure brightness and to do the calibrations and so forth. And they're very, very good programs. But wait a minute, we're talking about video photometry. They do not support video. So what do? Well, there's a way you can do it. And you can use video. It's a 2-step process. It's not that tough. Look at the next slide. This is how I analyzed the JE work we'll talk about tomorrow. First, you convert the video AVI file to JPEGs. You can pick another one, but you can use JPEGs. So you can use virtual dub. Probably everybody's used that. Use virtual dub, pick out 100 or 200 frames, convert them to JPEGs. It'll just export. It's in the export image sequence JPEG. So you create a set of 100 JPEGs. You then copy those JPEGs right into, say, MaximDL or CCD Soft. Then you can examine each one. You can look at every pixel in each one just by moving the mouse. It's really quick and easy. You can average them. You can process them. And you can graph the results if you want to. And you can save averaged results as a CSV, comma, separated variable file. So there are a lot of ways to do it that give you more power than you have available in LI and in Tangra. So this is using photometric software either in place of or to support LI and Tangra. Next slide, please. So whatever you do with the software and in your setup, you still have to be sure it's linear. I think you're probably getting that message. You have to be sure that it's linear. You must assure that you have a reference and comp object and account for all the errors. Now about linearity, next slide, please. How do you measure camera linearity? And this, again, Risto did a nice example in his write-up on his website. It is hard to do. Likewise, it's a great exercise. If you're going to do photometry and understand your camera and the system, this is a great thing to do. Probably one of the best ways is to get a star cluster, go ahead and video it. If you're using video, you got to video it. You then convert the video to JPEGs. Maybe you've got 200 JPEGs, put them into a photometric program, and then pick out 50 stars. You have to have a cluster. You can look up the 50 star brightness, identify the stars, measure, and compare the observed brightness of each star to the catalog brightness of each star, and then plot it. And this will tell you right away what your linearity problems are or not. This is important to do, but it's relevant only if you do it under the same conditions you're going to do the photometry. So if you've done this on, pick a number, 8th to 10th magnitude stars, and then you go look at the Jupiter moons at 5th magnitude, all bets are off. You have to do it in the general regime of what you're going to be doing photometry in. But this is an excellent way to get started on understanding what's involved in measuring intensity. Next slide, please. I did mention a comp object. Very important to do that. That'll correct for most of the astronomical or sky errors that I mentioned, like contrails and clouds and changing brightness, and even to some degree, movement of the star through or the object through the sky. You have to watch out for variable comp stars. As you said, I've discovered when I was doing a lot of asteroid light curves, at one point I discovered in 1 week, trying to do one asteroid, right? And in 1 week, I discovered 3 brand new variable stars because I picked them as comp stars. I kid you not. After I got the 3rd one, I said, Christ, I don't want these damn things. I'm trying to do the asteroid. And vermin of the sky, that's right. The other vermin, that's right. That's right. it was, some of them I've written up, some of them it's still work I need to follow up and get done and document and so forth. And you do have to, there are a lot of variable stars out there. And real cool eclipsing ones and stuff. Often, again with video, here's a price you pay with video. Because the dynamic range is so limited, and you may well not have a comparison star or star, for example, of a reasonable brightness in the field of view. So what do? You do have to move then to another field, some nearby field. Go-to scopes are great for that. Go to a nearby field, measure the comp star, come back, measure your object. Keep going back and forth. It's a pain in the neck, and then you've got a lot of data to keep sorted out, but it can be done. Next slide, please. So, minimum to-do list. And this is the link that I was talking about to the Tigris study. Read some how to do it photometry books. There are a lot of them around. And usually the manual that comes with the photometric software also gives you pretty good guidance. Try to do a couple of easy variable stars, like WW Ursa Major has a period of 6 hours or so and a swing of almost a magnitude. And if you can't get a good curve out of that, there's something wrong. But it's not just get a nice looking curve, get an accurate curve. If you can't do it accurately, if you don't know the values that you're ending up with, you're not doing photometry. You're just doing curves. So that's the key there. Be skeptical of the results again. Look at the AAVSO site and Minor Planet site and some of the others. And they'll give guidance as well. And by all means, study Ristos. Actually, I think it chopped off the left, but study Ristos' paper on his Tangra site. It really will be an eye-opener to you. If you think you understand your video camera, you won't sleep very well at night. You really won't. He did a wonderful job. He's a bright guy. I think that's the last slide. Oh, there we go. Oh, yeah, okay. Oh, we aren't going to 44, don't worry. I just put all my junk slides in the end, and so they're still available. Strongly consider, use video when it's needed, but only when it's needed. If you need the fast response and you can accept the limited dynamic range, sure, it makes sense. But use the CCD whenever possible. You get the wider range, et cetera, et cetera. So that's my cautions. And if any of you have questions, I'll be glad to answer now. I'll be around tomorrow too. So, okay, thank you very much. Yes. No. Oh, I'm not sure. Have I read have I read exoplanet observing techniques or no, I haven't. I've done a couple of exoplanets just for the heck of it, but I have not read that. Okay, very good. Well, if he's observing them, he's doing pretty well. Again, I don't know if he uses CCDs or video. Probably CCDs, because he doesn't have to use video, so he doesn't use them. Yes, Jay. That's correct. That's right.